Somewhere behind your eyes, right now, something is turning these words into meaning. That process feels like it is happening in a single, continuous now. One moment sliding into the next, smooth and unbroken, like water moving down a slope. Almost everything you do assumes that this feeling is accurate. You plan around it. You measure your life by it. You trust it more than you trust almost anything else you know. Tonight is about looking a little more closely at that feeling. Not to frighten it away, but to understand where it comes from, and what physics and biology have found when they went looking for the thing underneath it. It turns out to be a much stranger foundation than most of us ever pause to consider. Not stranger in a way that should worry you. Stranger in the way that a familiar hallway turns out to have a second, hidden room behind it, one that was there all along. Let's start gently with a simple question people rarely ask out loud. What is time? Try answering it without circling back to the word itself. It is harder than it sounds. Most definitions borrow the very thing they are trying to explain. This is not a new difficulty. People with extraordinary minds have run into the same wall for well over 2,000 years, and the wall has never really moved. The earliest serious attempt we still have comes from Aristotle. In ancient Athens, in a work called the Physics, he proposed that time is the measure of motion. It is an elegant idea, and for a long stretch of history, it felt like enough. If something moves, you can count how long it takes to get from one place to another, and that count is time. A shadow crawls across a sundial. A heart beats. You tally the beats, and you call the tally time. For roughly 2,300 years, that was a workable answer for almost every practical purpose. Then, in 1905, a young clerk working in a patent office in Bern, Switzerland, published a paper that quietly pulled the idea apart. His name was Albert Einstein, and the paper introduced what we now call special relativity. Einstein showed that motion and time are not independent of each other. They are tangled together. How fast something moves changes the rate at which time passes for it. This creates an odd little loop. Aristotle said time is what motion is measured by. Einstein showed that motion is itself measured using time. Each definition leans on the other, like two people using each other as the only chair in the room. Neither one can stand up on its own. Long before Einstein, in 1687, Isaac Newton published the Principia, the book that gave the world the mathematics of gravity and motion, and quietly underpins nearly everything engineered since, from bridges to rockets to the timing systems inside your phone. When Newton turned his attention to time itself, he wrote that time, in its own nature, flows evenly, without any relation to anything outside itself. It reads like a definition. Looked at closely, it is closer to a shrug dressed up in formal language. It says, in effect, that time simply flows on its own, without needing an explanation for why or how. A philosopher named Gottfried Wilhelm Leibniz read Newton's work and asked the obvious follow-up question: if time flows, what does it flow relative to? A river flows relative to its banks. A clock ticks relative to another clock. What is time ticking against? Newton did not have an answer, and neither did anyone defending his position. The two of them, along with an intermediary named Samuel Clerk, exchanged a now famous series of letters between 1715 and 1716, producing some of the sharpest philosophical writing of the era, and no resolution at all. Physics simply moved forward, treating time as a background stage on which events happen, without ever settling what the stage itself was made of. Centuries later, in the 20th century, a physicist named John Archibald Wheeler took a turn at the question. Wheeler is a significant figure in modern physics. He coined the term black hole. He supervised the doctoral work of Richard Feynman. He contributed to the design of early nuclear reactors, and he helped write one of the most important textbooks on general relativity ever produced. If any physicist of the last 100 years had the tools to give a clean answer, it might have been him. When someone asked him directly what time is, Wheeler offered this, half joking: time is what keeps everything from happening all at once. It is a charming line. It is not a definition. It captures something true about how time functions in our experience, without explaining what it fundamentally is. Now go back much further, to around the year 400, to a theologian named Augustine of Hippo, writing in Roman North Africa. In the middle of a book largely concerned with memory and faith, called the Confessions, he paused to consider the same question, and wrote something that has been quoted ever since. What then is time? If no one asks me, I know. If I wish to explain it to someone who asks, I do not know. A theologian in antiquity and a leading theoretical physicist in the 20th century arrived at essentially the same place, 1600 years apart, not because neither of them thought carefully about the problem, but because the problem itself resists this kind of direct definition. This is not a gap that is slowly closing as science advances. It has stayed remarkably stable across an enormous span of intellectual history. There is a way to sidestep the problem, and it is worth considering. Maybe time is not the kind of thing you define in words at all, the way you cannot really define the color red to someone who has never seen color. What you can do is measure it precisely and reliably, even without settling what it fundamentally is. And measuring time is something human beings have become extraordinarily good at. In 1967, the General Conference on Weights and Measures fixed the definition of a second using the cesium atom. 1 second was set as the time it takes for 9,192,631,770 oscillations of a cesium-133 atom, as it transitions between two particular energy states. That number looks arbitrary, but it isn't. It reflects a property of the atom itself, something that does not drift, does not wear out, and does not depend on where in the universe you happen to be standing. A cesium atom in a laboratory in Colorado oscillates at exactly the same frequency as one moving through deep space at half the speed of light by the 2010s. Timekeeping had advanced even further. Optical clocks built around strontium atoms reached a precision of about 1 part in a billion billion. A clock at that level of precision could run for the entire 13.8 billion year age of the universe and lose less than a single second. These instruments are so sensitive that lifting one by a single centimeter measurably changes the rate at which it ticks, because gravity itself is very slightly weaker a centimeter higher up, and the clock detects the difference. It is worth sitting with what these machines are actually doing. They are not measuring time directly, the way a ruler measures length directly against a fixed unit. They are counting oscillations of atoms, and we have agreed to call that count time. The vibrations are entirely real and extraordinarily well understood. The label we place on them, the word second, the word time, is a human convention layered on top. We have built instruments capable of measuring a billionth of a second with confidence, and we still do not have a settled answer for what, exactly, is being measured that naturally leads to a slightly different question, one that feels more solid. Even without a tidy definition, time clearly does something. It moves forward, coffee cools, eggs break and do not spontaneously reassemble. You get older, never younger. There is a direction here, something people often call the arrow of time, and it feels like the most dependable thing in ordinary experience. It turns out that this arrow is much less obvious at the level of fundamental physics than it is at the level of everyday life. In 1954, a physicist named Gerhard Ludus proved a result that a year later was extended by Wolfgang Pauli. Together, their work established what is now called the CPT theorem. It states that the fundamental laws of physics remain unchanged if you simultaneously reverse three things: electric charge, spatial orientation, and the direction of time. Flip all three together, and the equations still hold. Consider what that means for the individual laws. James Clerk Maxwell's equations for electromagnetism, written in the 1860s, work equally well if you run them backward in time. The Schrödinger equation, the foundation of quantum mechanics, behaves the same way. Einstein's equations for general relativity are symmetric too. A planet orbiting a star traces the same curve whether you play the motion forward or in reverse. Every fundamental law of physics discovered so far treats the forward and backward directions of time as mathematically equivalent. And yet nothing about ordinary life feels equivalent in that way. You age in one direction, memories form in one direction. An egg breaks and does not spontaneously reassemble into its shell. If the underlying laws genuinely do not distinguish forward from backward, where does the felt direction of time come from? The answer traces back to a physicist named Ludwig Boltzmann, working in 1872. He identified the concept of entropy as the source of the arrow. Though what entropy really describes is not disorder so much as probability. Picture a glass of water sitting intact on a counter. There is exactly one way for it to look that way, whole, with the water inside. Now picture it knocked to the floor. Shattered glass, water spread across the tiles. There are an enormous number of ways for that mess to be arranged. Far more than there are ways for the glass to sit there intact. Boltzmann's insight was that the universe does not have any particular preference for disorder. It simply has vastly more room for it. There are overwhelmingly more arrangements that count as messy than arrangements that count as neat. So if a system is free to change at all, it will almost always drift toward a messier, more probable configuration. That drift is the arrow. Coffee cools because heat has far more ways to spread out evenly than to stay concentrated in one place. A room fills with the smell of smoke because the smoke molecules have vastly more ways to scatter than to remain clustered near their source. Boltzmann formalized this as what is now called the H theorem, a proof that entropy tends to increase over time. For the first time, the arrow of time had a mechanism behind it. Boltzmann did not stop there, and what he found next turned out to be less comforting. If entropy explains the arrow, then the arrow is a consequence rather than a fundamental law, and a consequence needs a starting point to be a consequence of. For entropy to increase steadily from the beginning of the universe had to begin in a state of unusually low entropy, meaning unusually high order, everything unusually tightly and specifically arranged. Boltzmann spent much of his career building the entire field now called statistical mechanics, trying to explain why the universe would have started that way. He never found a satisfying answer. The starting condition simply had to be assumed. It was not, and still is not, something derived from a deeper principle. That gap sat mostly untouched for close to a century, until the year 2000, when a philosopher of physics named David Albert gave it a formal name in a book called Time and Chance. He called it the past hypothesis. Stated simply, the second law of thermodynamics, the law that entropy increases and gives time its felt direction, only works if you separately assume that the universe began in an extremely low entropy state. That assumption is not derived from anything more fundamental. It has to be taken as a starting axiom before the rest of the reasoning can proceed. How improbable is that starting condition? The physicist and mathematician Roger Penrose worked out an estimate. He asked, out of all the ways the early universe could conceivably have been arranged, how many of them would produce entropy low enough to give rise to the arrow we actually observe? His answer is not a number you can meaningfully picture. It comes out to roughly 1 in 10 raised to the power of 10 raised to the power of 123. To put that in perspective, 10 raised to the power of 120. 3 is already a number with more zeros than there are particles in the observable universe. Raising 10 to that already unimaginable power produces something that no ordinary description can capture. That number represents the improbability of the very starting condition responsible for your coffee cooling, and your memories pointing in the direction they do. Faced with a number like that, some physicists have wondered whether the question itself might be framed the wrong way around. In 2004, Sean Carroll, a physicist then at Caltech, working with a researcher named Jennifer Chen, proposed an alternative. Instead of assuming the universe began in a special, highly ordered state that then required an explanation, they suggested the universe began in the simplest state possible: maximum entropy, complete equilibrium, no structure and no gradient of any kind, nothing to distinguish one region from another, from that featureless starting point. In their model, random fluctuations can produce small pockets of lower entropy, and crucially, these pockets can form in 2 directions rather than 1. Picture a flat, level table with a shallow puddle of water sitting perfectly still. Nothing flows because there is no slope anywhere. Now imagine the table tilts very slightly in 2 opposite directions at once. Water would begin to flow both ways from the same starting point. In Carroll and Chun's proposal, the universe behaves similarly. 2 branches of increasing entropy emerge from a shared point of equilibrium, moving in opposite directions. Our observable universe, our sense of forward, is simply one of those 2 branches. On the other, an observer would experience their own arrow running the opposite way, and it would feel just as normal to them as ours does to us. If this model is correct, the arrow of time is not a fundamental law woven into the fabric of the universe. It is closer to a local feature, a consequence of which branch you happen to be standing on. Neither branch is more real or more correct than the other. There is another, related consequence worth sitting with for a moment. If the direction of time can vary depending on your position in the universe, perhaps the present moment itself is less universal than it feels. Right now, this instant feels like the one thing you cannot argue with. You are here in this moment, and that much seems undeniable regardless of what else turns out to be uncertain. It is worth looking closely at that feeling too, because relativity has something surprising to say about it. In that same 1905 paper, the one most people associate with the equation relating energy and mass, Einstein also worked out something about simultaneity that turns out to matter more here. 2 events that appear to happen at exactly the same time for you will not necessarily appear simultaneous to someone else. If that person is moving relative to you, this is not a trick of perception, and it has nothing to do with delays in how light reaches your eyes. It reflects something about the actual structure of space and time. Picture 2 lightning bolts striking at once, one hitting a tree to your left, the other hitting a tree to your right. Standing exactly between them, you see both flashes arrive at the same instant, so for you, they are simultaneous. Now picture a second observer, riding past on a very fast train. Because the train is moving toward one bolt and away from the other, the light from each one reaches that observer at slightly different times. From their point of view, one bolt struck first and the other struck second. Neither observer has made an error. There is no experiment that can determine which version is the truly correct one, because there is no special, universal clock sitting outside the universe that records the one true order of events. Each observer's present moment, their now, is genuinely their own. The two are equally valid, and no law of physics privileges one over the other. Change your velocity, and you change your now. 3 years after Einstein's paper, in 1908, a mathematician named Hermann Minkowski, who had once been one of Einstein's teachers, gave a lecture in Cologne building on this idea. Minkowski proposed that space and time are not genuinely separate things, being awkwardly related to each other. They form a single combined structure, a four-dimensional whole often called space-time, or sometimes described as a block. He put it directly: space by itself and time by itself are destined to fade into mere shadows, and only a union of the two preserves an independent reality. Think of a city you know well. The north side of the city does not stop existing simply because you happen to be standing on the south side. The streets you walked through yesterday have not vanished, and the streets you will walk through tomorrow already have a definite location and shape, waiting there in the structure of the city as a whole. The city simply is, all of it, at once. Regardless of where your attention happens to be focused at a given moment, Minkowski's block picture proposes something similar about time. Your birth exists somewhere within the block. So does your death, and so does this present moment, right now, as you take in these words. None of these is more real or more truly present than any of the others. The sense that you are moving through time, that the past is gone and the future has not yet arrived, is not, on this view, a property of the block itself. It is a property of you, of what it is like to be a limited observer experiencing one narrow slice of a much larger structure, one point at a time. This can sound like pure philosophy, an elegant idea confined to blackboards and lecture halls, disconnected from anything you could actually measure. But in 1971, two physicists, Joseph Haffel and Richard Keating, decided to test it directly using ordinary commercial airline flights. Their setup was straightforward. They placed 4 cesium atomic clocks, the most precise timekeeping devices available at the time, aboard commercial jets. 2 flights circled the globe traveling eastward, in the same direction as the Earth's rotation, and 2 traveled westward against it. A 5th clock stayed on the ground at the United States Naval Observatory in Washington, serving as the reference. The clocks flying eastward returned having lost 59 billionths of a second compared to the ground clock. The ones flying westward returned having gained 273 billionths of a second. These were not rough approximations. The results matched the combined predictions of special and general relativity within the margin of experimental error. The clocks had not malfunctioned. Nothing about turbulence, temperature, or cabin pressure explained the difference. Time itself, quite literally, had passed at a slightly different rate for clocks moving at different speeds and sitting at different altitudes, compared to a clock that stayed still on the ground. The scale of the effect at ordinary airplane speeds is tiny, a matter of billionths of a second, far too small to ever notice directly. But it is not zero, and the gap grows the closer you get to the speed of light. This same effect operates continuously, all around you, in a system almost everyone relies on without realizing it. There are around 24 satellites orbiting Earth at an altitude of roughly 20,200 kilometers, moving at about 3.9 kilometers per second, each one carrying its own onboard atomic clock. 2 separate relativistic effects act on those clocks at once. Because the satellites sit farther from the center of the Earth, gravity is weaker there, And general relativity predicts that clocks in weaker gravity run faster, gaining about 45 microseconds per day relative to a clock on the ground, because the satellites are also moving quickly. Special relativity predicts the opposite effect, a loss of about 7 microseconds per day due to their speed. Combine the two, and the net difference comes to 38 microseconds every single day. That might sound negligible, but this is the system behind the global positioning system, used by roughly 2 billion people every day. Whenever a phone calculates a location using signals and timestamps from at least 4 satellites, the math depends entirely on those timestamps being accurate to an extraordinary degree. If engineers did not correct for the 38 microsecond daily drift, positioning errors would compound quickly, reaching around 10 kilometers of error after a single day, and worse from there. So the correction is built directly into the system. Every timestamp broadcast by every satellite has already been adjusted to account for the fact that time simply does not pass at the same rate up there as it does down here. 2 billion people each day are relying on a piece of technology that quietly assumes the present moment is not one single, universal thing shared identically by everyone, everywhere. It depends on where you are and how fast you are moving, and it has been engineered into the palm of your hand. So the outside world, the world of physics, turns out to be far less settled about time than it feels. But there is still one place where time seems absolutely solid, inside your own head, right now. Close your eyes for a moment and you can feel it, a kind of flow, a current. The sense that this moment is happening and then it slips into the next one. Whatever the equations say, this experience itself feels immediate and undeniable. It turns out neuroscience has spent decades quietly examining that feeling too. And what it has found is that a great deal of what feels like a direct, live experience of time passing is, in fact, something your brain constructs after the fact. In 1983, a neuroscientist named Benjamin Libet designed an experiment to look closely at this. A person sits in front of a clock face with a single dot sweeping around it and is asked to flex their wrist whenever they feel like doing so, with no external cue, no countdown, just an internal decision to move. 3 things are measured: the electrical activity in the brain's motor cortex, the moment the person reports having felt the urge to move, based on where the dot was on the clock, and the actual physical movement of the wrist. Intuitively, the order should be, you decide. Then your brain acts on the decision. Then your wrist moves. Libet found something different. The electrical signal in the motor cortex appeared, on average, about 350 milliseconds before the person reported consciously deciding to move. The brain had already begun preparing the action before the conscious sense of choosing it had even arrived. The felt sequence, decide first, then act, is a reconstruction assembled after the fact, not a live report of what actually happened in the order it happened. Around the same period, researchers began looking at ordinary, everyday perception of the present moment, not just decisions. A neuroscientist named David Eagleman, working at Baylor College of Medicine in the early 2000s, found that what we experience as now is itself an edited product. The brain receives sensory information through several different channels, and those channels do not arrive at the same speed. Visual information tends to travel more slowly through the nervous system than sound does, and touch varies depending on how far a given nerve signal has to travel, from a fingertip or from a toe, for instance, depending on the sense and the part of the body involved. The delays involved can range from roughly 80 to 500 milliseconds, which is a meaningful gap, and yet you do not experience your senses arriving out of order. You do not see a glass shatter and then hear it a half second later. Your brain waits, gathering the slower signals, holding back the faster ones, and stitches everything together into a single unified now before presenting it to your awareness. There is a small perceptual glitch that reveals this process directly, called chronostasis. Look quickly toward a clock, and the second hand can appear to freeze, just briefly, for longer than it should before resuming its normal motion. What is actually happening is that your eyes were in motion during the saccade, the rapid eye movement toward the clock, and during that movement your visual system had no reliable image to work with. So it takes the first clear frame it receives once the eyes settle and stretches that single frame backward in time to smooth over the gap, pasting it over the blank period rather than admitting there was one. In 2002, a neuroscientist named Patrick Haggard at University College London ran a related experiment. A person presses a button and 250 milliseconds later a tone plays. A simple and clear sequence of cause and effect. Subjects were then asked to report when each event happened. Their answers were consistently off, and off in a specific, patterned way. People reported pressing the button slightly later than they actually had, and hearing the tone slightly earlier than it actually played. In effect, the brain pulled the two events closer together in time than they really were. Haggard called this temporal binding. Rather than passively recording the relationship between an action and its consequence, the brain appears to actively tighten that relationship, adjusting the felt timing to make cause and effect feel more immediately connected than the raw timing would otherwise suggest. Beneath all of this sits an actual physical rhythm. Neurons fire in coordinated, rhythmic patterns, and one particular pattern, called the gamma rhythm, cycling somewhere between 30 and 100 times per second, is closely associated with the felt experience of a continuous present. It behaves something like a refresh rate for conscious awareness, the pace at which the brain samples incoming information, assembles it into a coherent frame, and presents that frame to you as now. If that rhythm were perfectly fixed, you could argue that underneath all the reconstruction and editing, there was at least one stable, reliable anchor, a steady internal metronome keeping genuine time. But the rhythm is not fixed. In 2016, a team led by a researcher named Enrico Tagliazucchi published findings on how certain substances that alter brain chemistry affect this rhythm. Under those conditions, the normally synchronized gamma pattern becomes fragmented. Different brain regions speed up or slow down independently. The usually unified sense of a single ongoing frame breaks apart, and the felt experience of duration shifts along with it. Seconds can feel stretched into what seems like minutes, or collapse the other way. Something similar has been observed in long-term meditation practice. A study led by a researcher named Mark Whitman in 2015 found that experienced practitioners of Vipassana meditation show measurably different gamma activity patterns, along with a correspondingly altered subjective sense of duration, sometimes feeling slower, sometimes faster, depending on the depth of the practice. And a related shift shows up during moments of intense stress or danger, such as a car accident or a sudden fall, when people commonly report that time seemed to stretch, that a few seconds of an event felt like far longer, likely connected to a surge of attention and an increased rate of sensory sampling during those moments. Put together, this points toward something worth sitting with calmly rather than anxiously: the felt sensation of time passing. The thing that seems more certain to you than almost anything else in your life is generated by an electrical rhythm inside your skull, one that can be measurably shifted by chemistry, by trained practice, or by a sudden burst of fear. Physics, approaching the question from the outside. through equations and experiments, finds that time is not as fundamental as it appears. Neuroscience, approaching from the inside, through the structure of perception itself, finds that it is substantially constructed. Two very different fields, arriving at oddly compatible conclusions from opposite directions, that naturally raises the question of what happens at a level deeper than both of these, deeper than the brain and deeper than the everyday physics of clocks and airplanes. The quantum level. If time is genuinely fundamental anywhere in nature, it ought to show up clearly there. In 1978, John Archibald Wheeler, the same physicist who offered that joking definition of time, proposed a thought experiment known as delayed choice. It uses one of the simplest pieces of equipment in quantum optics, a beam splitter, a device that gives a single photon to possible paths to travel, left or right. If you place detectors at the end of each path, the photon behaves like a simple particle. It goes one way or the other, and you can determine which. But if, instead, you use mirrors to redirect both paths so they recombine, and place a second beam splitter at that meeting point, something different happens. The photon behaves like a wave, producing an interference pattern that only makes sense if it had, in some sense, traveled both paths at once. Wheeler's twist was to ask what happens if the decision of whether to insert that second beam splitter is made after the photon has already entered the apparatus and started its journey, while it is still in transit. Does the photon's earlier behavior, having taken one path or having taken both, depend on a choice made after the fact? This was purely a thought experiment when Wheeler proposed it. In 2007, a team led by a physicist named Vincent Jacques at the École Normale Supérieure in Paris built a real version using single photons, genuine beam splitters, and a random number generator to decide, after the photon had already passed the first splitter, whether to insert the second one. The results matched Wheeler's prediction closely. When the second splitter was inserted, the data was consistent with the photon having traveled both paths. When it was left out, the data was consistent with the photon having traveled just one. The choice, made after the photon had already entered the apparatus, appeared to determine what the photon had done earlier, rather than simply revealing something that had already been quietly settled all along. The experiment has since been repeated many times, in different laboratories, and no simpler explanation involving some hidden, unmeasured property of the photon has held up against the data. This connects to a deeper and older result. In 1964, a physicist at CERN named John Bell proved a theorem addressing a question that had troubled physicists, including Einstein, for decades. Could the strange correlations seen in quantum mechanics be explained by some hidden, deeper mechanism, one where ordinary cause and effect still applied underneath the apparent weirdness? Bell showed mathematically that no such hidden mechanism, consistent with certain very reasonable assumptions, could reproduce the actual statistical patterns predicted by quantum theory. In 1982, a French physicist named Élie Aspect tested this directly. He created pairs of entangled photons, sent them off in opposite directions, and measured a particular property of each. The results were correlated far more strongly than any prior agreement between the photons, made before they separated, could account for. Measuring one photon and finding it in a particular state instantly correlated with a specific finding for its distant partner, every time, without any detectable signal passing between them. Einstein was famously uncomfortable with this, once describing it as spooky action at a distance, and argued for most of his later career that quantum mechanics must be an incomplete theory, missing some hidden variable that would restore a more ordinary picture. Bell's theorem, combined with Aspect's experimental results and later refinements by researchers, including John Clauser and Anton Zeilinger, effectively closed that door. In 2022, the Nobel Prize in Physics was awarded jointly to Aspect, Clauser, and Zeilinger for this body of work. The correlations are real, and they do not appear to rely on anything traveling through space or through time between the two particles. It is not that the connection happens faster than light, it appears to operate outside the framework of time altogether. That observation opened an intriguing possibility. If entanglement does not require time to function, perhaps the relationship runs the other way. Perhaps time itself depends on entanglement. In 2013, two prominent theoretical physicists, Juan Maldacena and Leonard Susskind, proposed exactly that, in a conjecture now referred to as ER equals EPR. The initials refer to two separate 1935 papers, both involving Einstein. One, with a physicist named Nathan Rosen, described theoretical bridges connecting distant points in spacetime, now commonly called wormholes. The other, with Boris Podolsky and Rosen, described what we now call quantum entanglement. For decades, these were treated as entirely separate phenomena, one belonging to geometry, the other to quantum theory. Maldacena and Susskind proposed that they are, in fact, two descriptions of the same underlying thing. Every pair of entangled particles is connected by a wormhole, and every such wormhole is simply what entanglement looks like when translated into the language of geometry. Follow that idea a little further, and it suggests that space-time itself might not be a fixed container in which quantum connections happen to sit. It might instead be built up out of those very connections, emerging from a web of correlations that, at large enough scale, starts to look like distance, duration, and cause and effect. There is a specific mechanism that tries to explain how this emergence could actually work. Proposed in 1983 by two physicists, Don Page and William Wu. Their idea begins with the observation that a truly closed system, one containing absolutely everything with nothing external to it, is described in quantum mechanics by a single overall state. And crucially, that overall state does not change, because change requires a reference point outside the system to measure against. And by definition, there is nothing outside a system that contains everything, but split that total system into two parts. Call one part a clock, and call the rest of it everything else. The quantum correlations between those two parts, the way their respective states become entangled with each other, can behave exactly like the passage of time, from the perspective of the clock looking at everything else. The clock registers a before and an after and measures a gap between them. From inside that relationship, there is a meaningful experience of time passing. From outside the whole system, there is none at all. In 2013, a team led by a researcher named Ekaterina Mareva at the National Institute of Meteorological Research in Turin built a small-scale version of this setup using entangled photons in a laboratory. An observer positioned outside the entangled pair, looking at the system as a whole, measured no change, no sequence, and no duration. An observer entangled with one of the photons, measuring the other, registered a clear before and after, a genuine sense of change and duration. Same photons, same laboratory, same equipment, and two different experiences of whether time was passing at all, depending entirely on the observer's relationship to the system rather than on anything happening independently within it. There is a further variation of Wheeler's delayed choice idea, built in 1999 by two physicists at the University of Maryland, Yoonho Kim and Yanhua Shi, called the delayed choice quantum eraser. It uses a pair of entangled photons, One, called the signal photon, passes through a double slit and strikes a detector screen. Ordinarily, this produces the classic interference pattern associated with wave behavior, unless something reveals which slit the photon passed through, in which case the interference disappears and the photon behaves like a simple particle instead. The second photon, called the idler, carries information about which path the signal photon took. In this setup, the signal photon hits the screen and is recorded first, its data locked in. Only afterward is a choice made about what to do with the idler photon, either erase the which path information it carries, or preserve it. If the information is erased, sorting through the already recorded signal photon data afterward reveals an interference pattern after all. If the information is preserved instead, the same recorded data shows no interference. Nothing about the physical record on the screen changes after the fact. What changes is which pattern becomes visible once the data is sorted according to a decision made later. It suggests that the earlier recorded data was not, in fact, a single settled outcome all along, but something closer to a superposition of two possible outcomes, with the later choice determining which one becomes the effectively real one when you look back. A further step in this direction came in 2017, from a team led by Giulio Rubino at the University of Vienna in an experiment called a quantum switch. In ordinary experience, if you have two operations, A and B, one of them happens first and the other second. There is always some definite order, even if you personally do not happen to know what it is. Rubino's team arranged for the controlling system that determines this order to itself be placed in a quantum superposition. The result was a situation in which operation A effectively occurred both before and after operation B at once, rather than in one fixed order or the other. This is not simply an interpretation of the data. The setup produces a specific, measurable computational advantage that cannot be reproduced by running the operations in either fixed order or by randomly alternating between them. The advantage exists only when the order itself remains genuinely undefined. The experiment has since been reproduced in more than one laboratory with consistent results. At this level of physics, the statement A happened before B does not appear to have one single definite truth until a measurement forces it to settle on one. Taken together, these results describe a version of causality quite different from the simple, one-directional picture most of us carry around without ever examining it, rather than a straight line running from yesterday toward tomorrow. It starts to look more like a web, one in which later events can, in certain carefully controlled quantum settings, participate in determining what the earlier ones turn out to have been. All of this naturally raises a deeper question. What happens when you try to write down a single quantum description of the entire universe at once, rather than of some small, isolated system within it? In 1967, a physicist named Bryce DeWitt did exactly that, completing an idea that Wheeler himself had been developing for some time. The result is now called the Wheeler-DeWitt equation, and it attempts to describe everything that exists. Every particle, every field, every force, folded into a single quantum mechanical expression. The equation has a striking feature. There is no variable representing time anywhere in it. This is not an oversight or a simplification. When you write quantum mechanics for a genuinely closed system that contains literally everything, with nothing left outside it to serve as an external reference, the mathematics simply does not produce a time variable. It describes a universe in which nothing, in the ordinary sense, happens. Not a universe where change is slow or hard to detect, but one where the very concept of something happening does not apply within the equation itself. Everything the equation describes simply is, all at once. This is known as the problem of time in quantum gravity, and it has remained open since 1967. It sits at the center of one of the most significant unresolved tensions in physics. General relativity is built entirely around time as something dynamic, something that bends and stretches depending on gravity and motion. Quantum mechanics, when applied to the universe as a whole rather than to some smaller system within it, appears to erase time altogether. Both theories are individually confirmed to extraordinary precision, and for close to 60 years now, no one has found a way to fully reconcile them. 3 physicists working at the forefront of this problem have arrived at 3 quite different responses to it, and it is worth walking through each of their positions calmly, because none of them is a fringe view. All 3 come from people who have spent careers working directly on this exact question. The first comes from Carlo Rovelli, one of the founders of an approach called loop quantum gravity, one of the leading frameworks attempting to unify general relativity and quantum mechanics. In 2004, he published an essay titled, quite directly, Forget Time. His argument runs roughly like this. If you had complete information about a physical system, knowing the precise state of every particle and every field within it, you would not actually need a time variable to describe it. You could describe the whole thing purely in terms of relationships between different quantities. This variable correlated with that one, this state connected to that state, with no need to specify a before or an after. On Rovelli's account, a time variable only becomes useful when your information about a system is incomplete, when you are missing details about its precise microscopic state and are forced to fall back on a statistical description. In that statistical description, a parameter naturally appears that behaves like time, increasing steadily and giving you a workable sense of direction and duration. But on this view, that parameter is not a fundamental feature of reality. It is closer to a consequence of not having complete knowledge. Rovelli expanded this argument in a book published in 2017 called The Order of Time, which has since been translated into dozens of languages. The core claim is that time, as we experience it, is something like a blur that appears precisely because our view of the underlying physical relationships is not sharp enough to make out the fine structure directly. Sharpen that view, in principle, and the blur, along with the sense of time, would disappear. What remains, in Rovelli's picture, is not nothing. Relationships between variables still exist. Correlations still hold. There is a structure, sometimes described as a web of events, that persists even without a ticking clock sitting above it. A second physicist, Julian Barbour, took a further step and questioned whether even that remaining structure needs to involve any kind of sequence at all. In a book published in 1999 called The End of Time, Barbour proposed that the universe should be understood not as a sequence of events unfolding one after another, but as a vast collection of complete static configurations, each one a full snapshot containing the position of every particle, the state of every field, all at once, with no ordering among them at all. He referred to the space containing every possible such configuration as Platonia. In this picture, some configurations happen to contain structures that look like records of a past. Things like a brain full of memories, a fossil embedded in rock, light that appears to have traveled for millions of years. These structures exist within the given configuration itself, as part of the snapshot, rather than as evidence of an actual preceding sequence of events. On Barbour's account, the felt sense that time has passed, that yesterday genuinely happened, is a pattern that exists within a single frozen configuration, not a report arriving from an actual earlier moment. A third physicist, Smolin, co-founder of the Perimeter Institute for Theoretical Physics, arrived at a conclusion that runs in almost exactly the opposite direction. In a book published in 2013, titled Time Reborn, Smolin argues that time is not an illusion, and not merely a byproduct of incomplete knowledge, but the single most fundamental thing there is. His reasoning starts from the idea that the laws of physics themselves are not fixed and eternal, rather than being permanently written into the structure of the universe from the very beginning. They evolve over time, along with the physical constants that appear inside them. Things like the speed of light or the strength of gravity. What persists across all of that change, in Smolin's account, is time itself, functioning as the underlying container within which the laws and the constants inside them are free to shift. It is worth noticing what each of these three positions costs, because none of them is free. If Rovelli's view is closer to correct, time is not fundamental, but the equations describing reality remain fixed and eternal underneath it. If Barbour's view is closer to correct, both time and motion dissolve into a static structure, an outcome even more radical than Rovelli's. If Smolin's view is closer to correct, time survives as something genuinely real, but the price is that the laws of physics themselves become provisional rather than permanent. There is no available option among these three that leaves every part of the ordinary picture fully intact. Each one asks you to give something up. It is also worth hearing how some of the people working directly on this describe their own uncertainty, in their own words, rather than filtered through commentary. Sean Carroll, a physicist at Caltech, and one of the most widely read science communicators working today, said in a 2023 conversation about the nature of time that we do not currently know whether time is fundamental, and that he was not confident the question would be settled within the coming decades. That is a carefully qualified statement from someone deeply familiar with the relevant physics, and it reflects roughly where the field as a whole currently stands. Carlo Rovelli, in a 2018 interview, described his own reaction to seriously entertaining the possibility that time might not exist as a kind of vertigo, a genuinely disorienting feeling, even for someone who has spent decades working with the mathematics that points in that direction. These are not statements of confusion or failure. They reflect an honest engagement with a genuinely difficult open problem, from people who understand the relevant physics as well as anyone alive so far. All of this has stayed largely in the territory of equations, laboratory-scale experiments, and careful arguments among theorists. It is worth turning now to somewhere in the actual universe where time visibly runs into trouble, in a much more direct and physical way. In 1916, barely a year after Einstein published General Relativity, a German physicist named Carl Rovelli worked out an exact solution to Einstein's equations for a perfectly spherical mass. While serving on the Russian front during the First World War, he mailed the solution back to Einstein. What it described was a region where enough mass is compressed into a small enough space that the surrounding geometry curves so sharply that nothing, not matter, not light, not even information, can escape from within a certain boundary. That boundary is now called the event horizon. Time behaves in a genuinely strange way near that boundary. Picture watching someone fall toward a black hole from a safe distance. As they approach the horizon, from your point of view, their clock appears to run slower and slower. Their movements look increasingly sluggish, and the light coming from them shifts steadily toward red, then further into the infrared, eventually fading out of visible range entirely. From your vantage point, they never quite finish crossing the horizon. They appear to hang there, forever approaching but never arriving. From their own point of view, however, nothing unusual happens at all. They feel no barrier, notice no boundary, and continue falling through. their own clock ticking along completely normally the entire time. Both descriptions are correct, simultaneously, for their respective observers. Time is not simply slowing down at the horizon in some single, agreed-upon sense. It is behaving in two genuinely different ways for two different observers, and those two accounts do not need to be reconciled into a single story, because relativity does not require that they be. What lies beyond the horizon, further in, is stranger still. Inside a black hole, according to general relativity, the mathematical roles of space and time effectively trade places. Outside the horizon, you have freedom of movement in space, choosing to go left, right, up, or down, but no freedom at all regarding time. You move forward through it, always in one fixed direction. Inside the horizon, this flips. Movement toward the center becomes, in a mathematical sense, movement through time rather than through space. And just as you cannot choose to stop moving forward through time outside the horizon, you cannot choose to stop falling toward the center once you are inside it. In 1965, Roger Penrose proved that this process leads to a definite endpoint, work that later contributed to his share of the 2020 Nobel Prize in Physics. His singularity theorem showed that, under quite general conditions, gravitational collapse inevitably produces a singularity, a point where the curvature of spacetime and the density of matter both become infinite, and where every known equation of physics simply stops producing a meaningful answer. At the singularity itself, time does not gradually slow to a stop. It ceases to function as a meaningful concept altogether. There is no coherent notion of a next moment, because the word next itself depends on time continuing to exist in some usable form. And that is precisely what breaks down there. In 1974, Stephen Hawking added another twist. He showed that black holes are not permanent fixtures. They slowly evaporate. At the quantum level, pairs of particles and their corresponding antiparticles are constantly popping briefly into existence, throughout empty space and then annihilating each other. A completely ordinary process that happens everywhere. Near the boundary of a black hole, occasionally one particle from such a pair falls inward while the other escapes outward, carrying a small amount of energy away with it. Over an enormous span of time, this slowly drains mass from the black hole until, eventually, it disappears entirely. This process is now called Hawking radiation. For a black hole with roughly the mass of our Sun, the full evaporation would take somewhere on the order of 10 raised to the power of 67 years, a length of time that dwarfs the current age of the universe by a factor that has no everyday name. And yet the process would still, eventually, run to completion. This raises a genuinely difficult question. Everything that ever fell into a black hole, stars, planets, light, carried information about its own structure and history along with it, past the horizon toward the singularity, where time itself comes to an end. If the black hole then fully evaporates and disappears, leaving behind nothing but a faint, featureless glow of thermal radiation, what happened to all of that information? A foundational principle of quantum mechanics, called unitarity, holds that information should never be truly destroyed. That in principle, you should always be able to reconstruct an earlier state from a later one. If the black hole genuinely erased that information, this core principle of quantum theory would be violated. But the event horizon is, by definition, a one-way boundary. So it is not obvious how the information could have escaped either. Hawking argued for roughly 30 years that the information really was destroyed, and that quantum mechanics would eventually need to be revised to accommodate this. In 2004, he publicly reversed that position, conceding that the information likely does survive in some form, without offering a complete explanation of the mechanism involved. This is now known as the black hole information paradox, and it has remained an open problem in theoretical physics for roughly 50 years. Time appears to end inside a black hole. Whatever fell in, and whatever information it carried, apparently does not end along with it, though exactly how that turns out to be possible remains unresolved. It might be tempting to file black holes away as distant, exotic curiosities, the kind of thing that only matters at the far edges of the universe, well outside ordinary experience. But in April of 2022, the Event Horizon Telescope collaboration released an actual image, not a simulation or an artist's rendering of Sagittarius, a star, the supermassive black hole sitting at the very center of our own Milky Way galaxy, with a mass around 4 million times that of the Sun, located about 26,000 light-years from where you happen to be right now. Every star visible in the night sky, including the Sun, is in orbit around that object. And so, by extension, is the Earth, moving at roughly 230 kilometers per second, completing one full orbit approximately every 225 million years. The very same general relativity that quietly adjusts the clocks on GPS satellites also predicts, with complete consistency, that time itself effectively comes to a stop at the center of the object our entire solar system is gravitationally bound to and has been slowly circling for its entire existence. A black hole is, in the end, a local phenomenon, a specific location where the ordinary rules break down. It is worth asking whether time faces any kind of limit on a much larger scale as well, across the universe as a whole rather than just at one particular point within it. In 1852, a physicist named William Thomson, later known as Lord Kelvin, followed the second law of thermodynamics, the same law behind the arrow of time discussed earlier, out to its ultimate conclusion. If entropy reliably increases, gradients flatten out, and differences steadily disappear, then eventually, given enough time, the process should reach a limit. No more temperature differences left to equalize, no remaining gradient to flatten, no usable energy left to do any further work. Every point in space eventually reaches the same temperature. Every particle settles into roughly the same energy, and nothing further changes anywhere. Kelvin called this the heat death of the universe. It is a slow, quiet outcome rather than any kind of dramatic collapse. The point at which the universe becomes so completely uniform that the very idea of a distinct moment stops carrying any real content. Consider what that implies for time itself. If time, as Aristotle first suggested, is fundamentally tied to the measurement of change, and if Boltzmann was right that its direction tracks increasing entropy, then a state with no further entropy to increase is a state with no further change left to measure, and therefore no further direction left to point toward. Time in that state does not stop the way a moving object stops. Stopping implies something remaining there to have stopped. Instead, the concept of passing simply loses its content, because there is nothing left that could meaningfully be described as passing. This scenario has become considerably more concrete. Since 1998, when two independent teams of astronomers, one led by Saul Perl, the other by Brian Schmidt and Adam Rees, observed distant supernova and discovered that the universe's expansion is not just continuing, it is accelerating. All three shared the 2011 Nobel Prize in Physics for the discovery, something generally referred to as dark energy, a name that mostly just labels our uncertainty about its nature rather than resolving it, is steadily pushing galaxies apart from one another at an increasing rate. The observable universe currently contains something like 2 trillion galaxies, given roughly 100 billion more years. Essentially every galaxy outside our own local group, the small cluster containing the Milky Way, Andromeda, and a handful of smaller neighboring galaxies, will cross what is called the cosmological horizon. Beyond that horizon, a galaxy's recession speed effectively exceeds the speed of light. Not because the galaxy itself is moving through space faster than light can travel, but because the space between us and it is expanding faster than light can cross it. Once a galaxy passes beyond that horizon, its light will never reach us again, not eventually, and not with some future improvement in telescope technology. It becomes permanently, irreversibly invisible. The night sky, over an immense span of time, will go dark, not all at once, but gradually, one star and one galaxy at a time, until, eventually, an observer looking up from whatever remains of Earth would see only the Milky Way itself, alone in an otherwise empty and featureless void, with no remaining evidence that anything else had ever existed at all. There is a further and somewhat more unsettling implication if the block universe picture described earlier turns out to be the correct one. If Minkowski's four-dimensional structure genuinely captures how reality is organized, then heat death is not simply an event waiting somewhere far off in the future. It is a region existing within the very same overall structure that also contains this present moment. Picture a long road with a city somewhere off to the east and an open desert somewhere off to the west. Both already exist right now, regardless of which direction you happen to be facing, or which one you happen to be standing closer to at this moment. In the block picture, the early universe, your own life, and the eventual heat death are simply neighboring regions within one single four-dimensional structure, none of them more or less real than any of the others, and none of them waiting for the others to arrive. In 2010, Roger Penrose proposed a way that this ending might not actually be a true ending at all. In a theory called conformal cyclic cosmology, the reasoning runs roughly as follows. In the far future, once heat death is complete, all that remains are massless particles, essentially just photons. A photon moving at the speed of light has what is called zero proper time. It does not experience duration in any meaningful sense, and for a photon, its moment of emission and its moment of absorption are from its own reference frame, effectively the same moment. A universe consisting entirely of photons is therefore a universe in which nothing retains any working clock at all. And without any working clock anywhere, there is no remaining way to measure scale. The distinction between very large and very small effectively disappears. Penrose's insight was that, mathematically, an infinitely expanded, cold, scaleless universe turns out to be indistinguishable from an infinitely compressed, hot, scaleless point, the kind of state usually associated with a Big Bang. In this picture, the heat death of one cosmic era becomes, mathematically, the beginning of the next one, without requiring any additional energy or external mechanism to make the transition, precisely because time, in the ordinary sense, has already lost its meaning by that point. Penrose predicted that this process should leave a faint, detectable trace, gravitational waves from black hole collisions in the era before ours, appearing as subtle concentric ring patterns in the cosmic microwave background, the oldest light we can currently observe. Different research teams examining data from the WMAP and Planck satellite missions have reported conflicting results on whether these patterns actually appear, and the question remains genuinely open and actively debated within the field. Amid all of this evidence pointing toward time being less fundamental than it feels, there is one experimental result that points cautiously in the other direction. In 2019, the LHCb detector at the Large Hadron Collider at CERN observed a specific process involving the decay of particles called demesing, in which the underlying symmetry between forward and backward time genuinely breaks down, because of the CPT theorem described earlier. A violation of the related symmetry connecting matter and antimatter under mirror reflection is mathematically equivalent to a violation of straightforward time reversal symmetry. The LHCb result demonstrated a real, measurable asymmetry of this kind, a genuine, if small, preferred direction of time appearing directly within a fundamental physical law rather than emerging only statistically. But the effect is confined to a fraction of a percent, appearing in one specific type of decay of one specific type of particle, while every other known fundamental process in physics remains, as far as we can currently tell, fully symmetric under time reversal. The everyday arrow of time you actually experience, the one responsible for cooling coffee and aging cells and forming memories, does not appear to be connected to this particular, very narrow crack in the underlying symmetry, taken as a whole. This is roughly where the deepest level of physics currently stands on the question of time. General relativity treats time as dynamic, something woven directly into the structure of space-time itself, shaped by the matter and energy it contains. Quantum mechanics, in its standard formulation, treats time as a fixed external parameter, ticking along steadily outside the system it describes, entirely unaffected by anything happening within it. Both frameworks are confirmed to extraordinary precision in their own domains, and they cannot both be straightforwardly correct about something as basic as what time fundamentally is. Reconciling them in a single unified theory of quantum gravity has remained an open problem for around 90 years now. String theory has been one major attempt, producing an enormous landscape of possible mathematical solutions with no clear way, so far, to select among them. Loop quantum gravity has been another, removing time from its foundations and replacing it with a network of discrete quantum states, while still working to fully recover the smooth, continuous space-time of general relativity at larger scales. Other approaches, including causal dynamical triangulation and causal set theory, have made their own contributions without yet resolving the underlying tension. In roughly that same 90-year period, physics split the atom, put people on the moon, sequenced the human genome, detected gravitational waves directly, and photographed a black hole for the first time. And across all of that progress, the specific question of what time fundamentally is has remained essentially where it started before quantum mechanics existed at all. Physicists working purely within classical physics had already put considerable effort into precisely defining and measuring time, and it is worth taking a moment to look at that longer, quieter history, because it shapes almost everything discussed so far. Long before mechanical clocks existed, people measured time using the movement of shadows and the steady flow of water. Sundials, some of the earliest known timekeeping devices, trace back to ancient Egypt and Babylon, relying on the predictable movement of a shadow cast by the sun across a marked surface over the course of a day. Their obvious limitation was that they were useless at night or under cloud cover, which led to the development of water clocks, sometimes called clepsydre, which measured time through the steady, controlled flow of water from one container into another, a method used in ancient Egypt, Babylon, Persia, India, and China, refined independently across very different cultures over centuries. Mechanical clocks, driven by weights and gears rather than shadows or flowing water, began appearing in European monasteries around the late 13th century, largely to help regulate the fixed daily schedule of prayers. These early mechanical clocks were not especially accurate by modern standards, often drifting by up to 15 minutes a day, but they represented an important shift. Time was, for the first time, being measured by a self-contained mechanism rather than by observing something in the natural world directly. A major leap in precision came in 1656, when the Dutch scientist Christian Huygens built the first working pendulum clock, applying Galileo's earlier observations about the regular, predictable swing of a pendulum. Huygens's design reduced clock error from around 15 minutes a day down to about 15 seconds a day, a roughly 60-fold improvement in accuracy achieved with a single, elegant mechanical insight. Pendulum clocks remained the most accurate timekeeping technology available for roughly the next 250 years. The next major shift came from an entirely different physical principle. In the 1920s, physicists discovered that a quartz crystal, when an electric current passes through it, vibrates at an extremely stable and predictable frequency, a property called the piezoelectric effect. Quartz clocks, developed through the 1920s and 30s, could keep time far more precisely than any pendulum mechanism, accurate to within a few seconds per year rather than per day. Then, in the middle of the 20th century, timekeeping shifted from mechanical and electronic vibration to atomic vibration itself, culminating in the cesium-based definition of the second described earlier, adopted formally in 1967. Each of these shifts, from shadows to flowing water, two swinging pendulums, two vibrating quartz, two oscillating atoms, represents the same underlying human project, carried out across many centuries and cultures, finding something in nature that repeats with enough reliability that you can use its repetition as a shared unit against which everything else can be measured. Notice, though, that at every single stage of this long history, what was actually being measured was always some physical process, a shadow's position, a water level, a pendulum's swing, a crystal's vibration, an atom's oscillation, rather than time in any more direct or fundamental sense. The process was always the reliable, measurable thing. Time was always the name given to counting it. A closely related history runs through the study of heat and energy, and it connects directly back to the arrow of time discussed earlier, long before Boltzmann connected entropy to probability. A French engineer named Sodi Carnot in 1824 was studying the theoretical limits of steam engines, trying to understand how efficiently heat could be converted into useful mechanical work. Carnot showed that no engine could ever be perfectly efficient, that some portion of heat energy would always be lost rather than converted into work, regardless of how cleverly the engine was designed. This became an early version of what would later be formalized as the second law of thermodynamics. A few decades later, in 1850, a German physicist named Rudolf Clausius refined Carnot's work and gave the underlying quantity a name, entropy, from a Greek root loosely meaning transformation. Clausius showed that in any real physical process, total entropy in an isolated system either stays the same or increases. And it was this exact principle that Boltzmann later connected to probability and to the direction of time itself, and that Kelvin, working independently around the same period, followed forward to its ultimate long-term conclusion in the idea of heat death. It is a nice illustration of how scientific ideas tend to develop, not through a single sudden breakthrough, but through a long relay of contributions. An engineer studying steam engines, a physicist naming a quantity, another physicist connecting that quantity to probability, and a fourth following the logic out to its most distant consequence, each building carefully on work that came before. There is also a quieter, related thread running through the physics of antimatter that connects back to the question of time's direction at the smallest scales. In the late 1940s, the physicist Richard Feynman, working with ideas originally proposed by his doctoral advisor, John Wheeler, described a way of mathematically treating a positron, the antimatter counterpart of an electron, as being mathematically equivalent to an ordinary electron moving backward through time. This is not generally interpreted as meaning that antimatter literally travels backward through time in any experiential sense. It is, instead, a mathematical convenience that happens to work out cleanly within quantum field theory, precisely because, as the CPT theorem discussed earlier makes clear, reversing charge and reversing time are deeply and mathematically related operations. It is a small, technical detail, but it is a good example of how thoroughly the question of time's direction is woven into the deep mathematical structure of modern physics, showing up in places that have nothing obviously to do with clocks, entropy, or cosmology at first glance. It is worth also spending a little time on how we came to understand the very beginning of the universe, since so much of tonight's discussion of entropy, the past hypothesis, and the arrow of time depends on there having been a definite beginning at all. In the 1920s, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made a series of careful observations of distant galaxies and found something unexpected. Nearly all of them appeared to be moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, provided the first strong observational evidence that the universe as a whole is expanding, rather than existing as a fixed, unchanging backdrop, as had generally been assumed before that. If the universe is expanding now, then, running the logic backward, it must have been smaller and denser in the past, and further back still, denser again, approaching some kind of extremely hot, dense, and compact state at the very beginning. A Belgian physicist and Catholic priest named Georges Lemaitre had actually proposed something along these lines slightly earlier, in 1927, describing what he called a primeval atom, from which the universe's subsequent expansion could be traced. The term Big Bang itself was coined somewhat dismissively in 1949 by the astronomer Fred Hoyle, who favored a competing steady-state model in which the universe had no beginning at all and had simply always existed in roughly its current form. Ironically, the term stuck, and the theory it was meant to mock eventually won out. The decisive piece of supporting evidence arrived in 1965, somewhat by accident. Two radio astronomers, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, were using a large horn antenna and kept detecting a faint, persistent background noise, evenly distributed across the entire sky, that they could not eliminate no matter how carefully they checked their equipment for faults. They had, without initially realizing it, detected the cosmic microwave background, the faint afterglow of radiation left over from a period roughly 380,000 years after the Big Bang, when the universe had cooled enough for light to travel freely for the first time. This radiation, remarkably uniform in every direction, with only extremely tiny variations, has since become one of the most important and precisely studied pieces of evidence in all of cosmology. And it is the very same faint signal that Roger Penrose has examined closely while searching for the concentric ring patterns predicted by his conformal cyclic cosmology model. Since that discovery, a series of increasingly sensitive space missions, including the Cosmic Background Explorer in the 1990s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck Satellite in the 2010s, have mapped this background radiation with ever finer precision, allowing cosmologists to work out an increasingly detailed timeline of the universe's history. From an extremely brief period of extraordinarily rapid expansion just after the beginning, known as inflation, through the formation of the first atoms, the first stars, and the first galaxies, all the way up through billions of years of subsequent development, right up to the present. Ongoing acceleration discovered through supernova observations in 1998. It is genuinely remarkable that human beings, using instruments built within the last century, have managed to reconstruct a reasonably detailed account of events stretching back roughly 13.8 billion years, based almost entirely on careful analysis of light. And yet, even with all of that detailed knowledge about how the universe evolved after its earliest moments, the deeper question of why it began in the specific, highly ordered, low entropy state that Boltzmann and later Penrose puzzled over remains genuinely unresolved. We can describe, with impressive precision, what the universe was doing a fraction of a second after the beginning. We still do not have a settled explanation for why that beginning took the particular form it did. There is active, ongoing experimental work today that is directly relevant to the deeper questions discussed earlier. And it is worth closing with a look at where some of that current research actually stands. Because the story is not a finished one. One active area involves searching for signs of quantum behavior in gravity itself, something that has never been directly observed in a laboratory. A proposed experiment, generally referred to as the BMV experiment, named after the physicists Sugato, Bose, and Chiara Ma, who, along with others, developed a theoretical proposal around 2017, aims to test whether gravity can produce entanglement between two small masses, in a setup that would provide direct evidence that gravity itself has a quantum nature. Something current theory strongly suggests, but that has never been experimentally confirmed. Experimental groups in several countries are currently working to build the extraordinarily sensitive equipment such an experiment would require, though a working version has not yet been completed. Another active area involves increasingly precise tests of relativity itself, extending the logic of the Huffle-Keating experiment described earlier into space. A mission called the Atomic Clock Ensemble in Space, developed by the European Space Agency, is designed to place extremely precise atomic clocks aboard the International Space Station, allowing scientists to test general relativity's predictions about time, dilation with far greater precision than has previously been achievable, and to search for any subtle deviations from Einstein's predictions that might hint at new physics. Meanwhile, work on the theoretical side continues across multiple competing approaches to quantum gravity, including ongoing refinements to loop quantum gravity, continued development of string theory and its proposed landscape of possible solutions, and newer approaches, including asymptotically safe gravity and various forms of causal set theory, each attempting, from a different angle, to find a consistent way to describe both the smooth, dynamic time of general relativity and the very different, non-dynamic time, or absence of time, that appears to arise naturally out of quantum mechanics applied to the universe as a whole. None of these efforts has yet produced a decisive, broadly agreed upon answer that is a genuinely accurate description of where things currently stand, not a failure of the scientists involved, and not evidence that the question is somehow unanswerable in principle. Difficult scientific questions have, throughout history, often remained open for long stretches before eventually yielding to some combination of better theory, better instruments, or simply a shift in perspective that made the existing evidence click into place in a new way. The question of what time fundamentally is, and why it seems to move in only one direction, has been open for a very long time by ordinary standards. It has not been open forever, and there is no strong reason to assume it will remain open forever either. There is another discovery worth mentioning, because it offers direct physical evidence that space-time itself, the very fabric whose bending underlies so much of what has been discussed tonight, is not simply a passive background, but something that can genuinely ripple. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, generally known as LIGO, made the first direct detection of gravitational waves, tiny ripples in the structure of space-time itself, produced by the collision of two black holes roughly 1.3 billion light-years away. Einstein had predicted the existence of such waves back in 1916 as a direct consequence of general relativity, but had also suspected that they would be far too faint ever to detect directly. The signal LIGO detected stretched and compressed space by an almost unimaginably small amount, roughly 1 part in a billion trillion, requiring detectors sensitive enough to measure a change in distance far smaller than the width of a proton across kilometers-long instruments. The detection earned a share of the Nobel Prize in Physics in 2017 for Rainer Weiss, Barry Barish, and Kip Thorne. Since that first detection, dozens of further gravitational wave events have been observed, including collisions between black holes and between neutron stars, opening up an entirely new way of observing the universe that does not rely on light at all. These waves are, in a very direct sense, ripples in the same four-dimensional structure that Minkowski described in 1908. Physical evidence that the fabric containing both space and time is not fixed and rigid, but capable of genuine, measurable motion of its own. It is also worth pausing on how differently various human cultures across history have conceived of time itself, since so much of tonight's discussion has focused specifically on the way modern physics frames the question, the framework of a single, forward-moving arrow of time, a line running from a fixed past through the present toward an open future, feels natural to most people raised within a broadly Western intellectual tradition. But it is not the only way people have organized their understanding of time throughout history. A number of ancient cultures, including certain schools of thought within ancient Greece, various Indian philosophical traditions, and a number of Mesoamerican civilizations, including the Maya, developed cyclical models of time instead, in which history is understood as repeating in great recurring cycles, rather than proceeding along a single unrepeated line from a beginning toward an end. The ancient Hindu concept of a kalpa, for instance, describes an enormous cyclical unit of cosmic time, involving repeated cycles of creation and dissolution on a scale of billions of years, developed entirely independently of anything resembling modern cosmology, yet echoing, in a general and appropriately cautious sense, some of the same intuitions explored by conformal cyclic cosmology far more recently. This is not meant to suggest any direct connection between ancient philosophy and modern physics. It is worth noting simply because it shows that the question of whether time is fundamentally linear, cyclical, or something else entirely is a very old and very widespread human question, one that different cultures have approached from entirely different starting points and, at times, arrived at strikingly similar structures, even something as apparently mundane and settled as the standardization of clock time across different regions has a genuinely interesting history behind it, one directly connected to the relativity of simultaneity discussed earlier, before the widespread adoption of railroads in the 19th century. Most towns and cities kept their own local time, generally set according to when the sun reached its highest point directly overhead, which meant that noon in one town could be several minutes earlier or later than noon in a town only a short distance away. This posed a serious practical problem once railway schedules needed to be coordinated across long distances, since a train timetable simply could not function reliably if every station along a route used a slightly different definition of what time it currently was. In 1884, an International Meridian Conference held in Washington, D.C. established a global system of standardized time zones based on the prime meridian running through Greenwich, England, effectively imposing a single, shared, artificial structure of simultaneity across the entire world for the specific and practical purpose of coordinating trains, and later telegraphs, aviation, and eventually global communication more broadly. It is a useful reminder that even our most basic, everyday sense of what time it is right now, something that feels almost entirely natural and given, is itself a relatively recent human invention built for practical convenience, layered on top of a much deeper physical reality in which, as Einstein would later show, there was never actually a single, truly universal now to begin with. One further connection is worth drawing out, tying back to the singularity discussed earlier in the context of black holes. Roger Penrose's 1965 singularity theorem was originally developed to describe what happens inside a collapsing black hole, but very similar mathematics, developed jointly with Stephen Hawking in the years that followed, applies just as directly to the very beginning of the universe itself, run in reverse. Just as a sufficiently massive collapsing star inevitably reaches a singularity, where the equations of general relativity break down, the Hawking-Penrose singularity theorems, developed through the late 1960s and early 1970s, showed that, under quite general assumptions, an expanding universe like ours, traced backward in time, similarly leads to a singularity, a point at which the same equations again cease to produce meaningful answers. In other words, the same underlying mathematics that describes time coming to an end at the center of a black hole also, when run the other direction, describes time apparently beginning at the singularity now generally referred to as the Big Bang. This does not mean the beginning of the universe and the center of a black hole are literally the same kind of object in every respect, but it does mean that general relativity, on its own, is fundamentally unable to describe what actually happens at either boundary. In both cases, it is widely expected that a full theory of quantum gravity, once it exists in a complete and tested form, would replace the troublesome singularity with some kind of smoother, well-behaved quantum description. This remains one of the clearest and most concrete reasons that resolving the problem of time in quantum gravity actually matters beyond pure theoretical curiosity. It is not simply an abstract puzzle confined to blackboards and philosophy seminars. It sits directly at the heart of understanding both how the universe began and what genuinely happens inside the black holes scattered. Throughout it, it's worth mentioning one more thread, since it touches on a very different, more human-scale version of the same underlying puzzle. Quite apart from physics and neuroscience, psychologists have studied what is sometimes called subjective time dilation, the ordinary, everyday sense that time seems to speed up or slow down depending on what you are doing, without any of the exotic ingredients discussed so far. No black holes, no entangled photons, no relativistic speeds involved at all. A commonly reported pattern is that time feels like it passes quickly during periods filled with novel, engaging experiences, and slowly during periods of boredom or repetition, while afterward, in memory, the pattern often reverses. A week spent traveling somewhere new, packed with unfamiliar sights and experiences, tends to feel like it passed quickly while you were living through it, but tends to feel, in retrospect, like it lasted far longer than a week spent at home doing the same familiar things day after day, which often feels the opposite way around, dragging in the moment but compressing almost to nothing once it is behind you. Researchers studying this effect, including work summarized by psychologists such as Claudia Hammond in her book Time Warped, published in 2012, generally trace it back to how densely memories get encoded. Novel experiences tend to generate a larger number of distinct memories, and when you later try to estimate how much time a period took, your brain appears to rely heavily on how much memory content is associated with it, rather than tracking actual elapsed duration directly. More memories, packed closely together, tend to produce the retrospective impression of a longer stretch of time, even when the actual number of days involved was identical to a far more forgettable, and therefore apparently shorter feeling, comparable period. This adds one more layer to everything already discussed about the brain's role in constructing the felt experience of time. It is not just that the brain assembles a live sense of now from staggered sensory inputs, as Eagleman's work showed, or that it reorders decisions and actions after the fact, as Libet demonstrated. It also appears to retroactively judge how long a given stretch of your life felt, based substantially on how much you happened to remember from it, rather than on any kind of direct, continuously running internal stopwatch. Your sense of a week, a year, or a decade having felt long or short is, in this light, less a report on actual elapsed duration and more a kind of memory density, calculation performed well after the fact. It is worth returning, briefly, to something mentioned earlier regarding how information theory intersects with all of this, because it offers one more genuinely useful way of thinking about the arrow of time, distinct from the purely thermodynamic picture developed by in the late 1940s, an engineer and mathematician named Claude Shannon, working at Bell Labs, developed what is now called information theory, originally to solve a fairly practical problem involving how to transmit signals reliably over noisy communication channels. Shannon defined a precise mathematical measure of information content, and it turned out, somewhat surprisingly, to be mathematically identical in form to Boltzmann's much earlier definition of thermodynamic entropy, despite having been developed for an entirely different purpose in an entirely different field. Roughly 70 years later, this connection is not merely a mathematical coincidence. Physicists, including Rolf Landau, working at IBM in the 1960s, and later Charles Bennett, showed that there are genuine physical costs associated with processing and erasing information, directly tying abstract information theory back to the concrete physics of heat and energy that Boltzmann and Clausius had worked out a century earlier. Landau's principle states that erasing one bit of information in a physical system necessarily releases a minimum amount of heat into the surrounding environment, connecting the seemingly abstract world of computation directly to the same thermodynamic entropy responsible for the arrow of time. This has led some physicists, including a modern line of research sometimes associated with the broader field of quantum thermodynamics, to explore the idea that the arrow of time might be understood, at a very deep level, as fundamentally an information theoretic phenomenon tied to the gradual, irreversible loss of accessible information about a system's precise microscopic state, rather than purely a matter of energy or heat considered in isolation. It is, in a sense, one more version of Rovelli's argument that time may be closely related to incomplete knowledge, but arrived at from a completely different direction, through the study of computation and communication rather than through relativity or quantum gravity. What can be said with real confidence? Gathering together everything covered tonight, is this: time has no single, complete, non-circular definition. And this has been true for as long as people have seriously tried to write one down. Its felt direction traces back to an extremely specific, and so far unexplained, starting condition in the very early universe. The present moment, the sense of a single shared now, depends measurably on your speed and your position within a gravitational field, and is not something all observers necessarily share. A great deal of your subjective experience of time passing is actively constructed by your brain, assembled from fragments of sensory information that do not arrive in a single unified now, but very much feel that way by the time you notice them. At the deepest quantum level currently accessible to experiment, the ordinary sense that causes must always precede their effects does not hold up in every situation that has been tested, and the two most successful theories in the history of physics, general relativity and quantum mechanics, continue to disagree in a very basic and unresolved way about whether time is fundamental at all. None of this needs to be unsettling in the way it is sometimes framed. It is, instead, a fairly accurate and genuinely fascinating summary of how much careful, patient work has gone into understanding one of the most ordinary seeming features of everyday life, and how much of that work has turned up genuine surprises rather than simple confirmations of what already seemed obvious. The scientists whose work this covers are not standing at the edge of some frightening unknown, quietly withholding something from the public. They are simply doing what scientists generally do when they run into a genuinely hard problem, describing exactly what they have found, being precise about what remains uncertain, and continuing to work on it, one careful experiment and one careful argument at a time. You, meanwhile, are here, taking this in whatever sense of here and now turns out to be the most accurate one. Whatever the final answer to the nature of time eventually turns out to be, and whenever, if ever, it arrives, it is unlikely to change very much about how your own life actually feels from the inside, moment to moment. The coffee will still cool. The morning will still follow the night. And the quiet, ordinary business of living inside whatever time actually is will carry on, largely unaffected by how the deepest equations eventually settle the question. That seems like a reasonable place to let this rest for tonight.